Ну что ж, добро пожаловать на нашу презентацию. Поговорим о итерациях на границе. Меня зовут Лулей, и я исследователь, который занимается безопасностью в среде Java. А это мой партнер Хошин. Он является исследователем в области безопасности в облаке, в средах Kubernetes и так далее. И Ван Ли также нам помогал. Это старший инженер по безопасности в нашей компании. Я хочу рассказать вам о наших исследованиях. Когда мы начинали, я не очень много знал о ядре Linux. Это было достаточно странно. Вы можете удивиться, почему я занялся этими исследованиями. Я занимался аудитом кода для самых разных приложений, написанных на самых разных языках, включая Java, PHP, JavaScript и так далее. И в прошлом году я решил, что пришло время заняться чем-то более сложным. Это вот программа моего выступления. Мы начнем с мотивации, с того, что стояло за этим исследованием, с базовых идей. После этого мы поговорим о основах OOB и B-кэшецах. Рассмотрим ряд конкретных примеров. И в конце концов подведем итог, сделаем определенные выводы.
First, we are more familiar with file systems in our daily work. Second, most of file systems run in OS kernel, so bugs in these file systems may cause devastating errors. And third, take a look at this figure. We take XFS as an example. New features means more code, so more new code means a great chance of fighting bugs. But what about the real possibility? Before we started, we reviewed commits in file systems and found that bugs still existing in many famous file systems in the past year, such as AST4, BTRFS, and NTFS3, and we think it's possible. So where to begin? We started three previous works, and the second and third are both based on the first one. The first work is fuzzing file systems via two-dimensional input space exploration, which released a fuzzer called Janus. The two-dimensional input space here are disk image and file operations, while mutating sequence of file operations is relatively easy. But a disk image is a large binary blob that is structured and complicated, and existing fuzzers mutate only non-zero chunks in the image. However, mutating metadata blocks is more effective than mutating data blocks, but fuzzers do not have any knowledge about image layout and also fail to fix any metadata checksums. So Janus implemented metadata parsers for different file systems and found many bugs that can be triggered by mail phone images. So for this reason, we think metadata in disk image is still a vulnerable attack surface. Yeah, then I will hand over to Guoxin, and he will introduce the metadata that we focus on and detail the first out-of-bounds bug we discovered.
Okay, I will continue to walk through the metadata 101 and how we discovered the first out-of-bounds bug in Bcache-FS. So what is metadata? If we think of hard drive as a library, the metadata plays the role of recording the number of bookshelves, the location and category of each book, and even information for disaster recovery. In short, metadata is used to describe and manage file systems, but it doesn't include the content of files. Let's focus on four types of our related metadata: sweep block, log recall, directory entry, and XTTR. So first, sweep block. It's like control center for file systems. The primary Superblock resides at a fixed location and copies are stored at different locations for redundancy and recovery. You can locate these superblocks using a specific magic number, and superblock records variable information about file systems, such as sector size, block size, and some information about inode, like size, counts, and the root inode number, and so on. And then to recall file operations, we need log records. Log records are used by transaction logging to provide crash recovery capability. A record typically contains members such as operation type, transaction ID, associated inode number, and time. To describe different operations, the size of each record is variable. So log record table looks an array of various sized elements. Each element contains a record length member that indicates the size of its variable part. The next one is direct entry. When you run ls command to view the content of a directory, what you are actually seeing comes from directory entry stored in the main data. And the layout is similar to that of log records. It's quite easy to understand because file or directory names can vary in length. The size of each entry is also variable. And the last metadata type we will cover is XTTR. In addition to file permissions, owners, modification time, and other common file metadata, file system also supports extended attribute called XTTR. It looks like user-defined properties for file or directory. Look at this figure. We can use getFTTR command to list all XTTR file, or use setFTTR to cite one. Now you may have noticed that all the metadata types we are discussing, except for superblock, follow a layout that looks like an array of variable size elements. The superblock usually doesn't follow this pattern, but there are some exceptions in some specific implementations. We'll go into more detail later, but for now, what's important to keep in mind is working with such arrays, we need to pay attention to boundary consistency issues. So now, if there is a bug in the metadata, it should be clear that we need to mount a crafted image to trigger it. Metadata parsing work happens during the mount process. Typically, the mount operation requires a cap sysdomain capability. However, there is an exception. A file system can declare self-safe use with user space by using the fs user space mount flag. But unfortunately, most file systems do not support this flag. By default, pocket rules in the latest Ubuntu allows user with an active local station to mount an image. So it's true that desktop or even server environment allow regular non-privileged user to mount and auto-mount file systems. All right, all of that covers the foundational knowledge you need to understand what we will be discussing next. And I will talk about an OOB in Bcache, which is our first bug. So why did we choose Bcache FS as our first target? Well, it was contribute to the Linux 6.7 at the end of October 2023. It's quite new and complex file systems, which make it a great candidate for us to discover something interesting in the metadata. This OOB bug occurs in the superblock. As we mentioned earlier, we can use a magic number to locate the primary block and its copies. The implementation of this block is defined as a structure called BCHSB. Unlike other file systems, this block is split into two parts, a fixed part and a variable part. It uses the flexible array member to describe the variable part. The size of operate give the size of the structure as if the flex array member were empty. So it's common to use a fixed member to indicate the size of variable part for the allocation. For simplicity, we call this member length 1. The variable part of the sweep block contains many fields of different types. Each field starts with a common structure called BCHSB field. We can use container of micro to get actual field. The BCHSB field also has a variable part, and the size member, we called it length 2. So now we have two length members. The first one is length 1, which is used to calculate the total size of entire sweep block. And the second one is length 2. It's used to calculate the size of a single field. The actual field we focus is the clean field, corresponds to a BCHSB field clean structure. Again, this structure has a variable part which contains an array of G-sides, a G-side entry. Now take a look at the definition of the G-side entry. Familiarize a variable part and the size member, we call it length 3. So far, the layout might be a little bit complicated because this implementation makes heavy use of flexible arrays. One of the nerds. Here's an overview. We have left out the less important part and we only focus on the variable part and each level. There are 3 nettest levels. The first is entire sweep block. The second is an array of fields, and the third is an array of entries in the clean field. As we can see, if the clean field happens to be the end of the field, the iteration at every level will end at the same point, which is the end of the sweep block. Actually, there are 4 nettest levels in total. The first level is the array of keys in each entry. And it's important to do boundary check during iteration at each level, so that all the ends line up correctly, and there is no risk for an out-of-bounds bug. So let's dive into the iteration code. The function BCH2SB clean validate later. The function enters through the entries in the clean field. It checks whether the start of each entry is within the memory range of the clean field. This condition is very common in for loops. Most people write it in this way. However, the key point is that it just checks the start of the entry. So we still need to do an extra boundary check before accessing the member of an entry. Next, the function journal entry between keys validate will be called. This function iterates through all the keys in an entry. The where condition checks whether the start of each case reaches the end of the entry. During each iteration, it calls journal validate key function, which accesses the member of a key directly without any further checks, just like the previous function. The condition itself isn't the problem. When everything works as accepted, all the conditions are satisfied and all the iteration ends normally. Now let's put 2 conditions together. These 4 levels end at the same point in memory, but here is a problem. It accesses a member of an entry or even a key without making sure there is enough space in the first place. So if the end of the last entry is not equal to the end of the clean field, accessing the last key in the entry probably leads to an out-of-bounds bug. But there are still 2 questions we need to figure out. The first one is, where is the memory boundary? In the function BCH2 read-through block clean, it calls kernel memory duplicate function to allocate the memory for each clean field and its parameter is length 2. So the clean field is location independent. If the allocation is based on the type level, and the location size is an entire sub block, and we need one more step to trigger this out-of-bounds bug, which is placing the clean field to the last position. The second thing we need to check is we need to figure out if there are any check functions. Right now, we didn't see any checks during iteration, but it's possible the check was already done before. And we focused a function, and we found a function called bch2sb clean validate. It only ensures there is not enough space for the fixed part of the clean field. That's it. So when we access the key in the last entry, it triggers out-of-bounds bug. And because of weird error handling, it ends up getting stuck in an infinite loop, like on local doors. Actually, we can also trigger this out-of-bounds on the last entry. It happens in another function. If you are interested, feel free to try building the POC yourself. Okay, let's summarize the 3 insights that can lead to this kind of out-of-bounds bug. So first, we need to determine the memory boundary. We must clearly understand where the iteration occurs. In some cases, allocation might be based on the page size, and default the target layout isn't reached the end of the memory. So we need to place it in the right place. This could be why such bugs are difficult to find by fuzzers, because mutation often happen on the original layout. Second, we need to identify the array of variable size elements, which is vulnerable layout we focus on. And there may be a size consistency issue. Third, there is no check code during iteration. If there is, it's not fully considered. We will talk about this case later. All right, this is the first bug we found at the start, along with some key insights we learned from it. And I'm going to give the stage to my partner, Luli.
Thank you. Guoxin summarized 3 key insights from the first bug. And after that, we wanted to check whether other file systems might have similar issues. So we implemented image parsers for the specific layouts we were interested in and across different file systems. And finally, we discovered 14 bugs in 7 file systems, 13 of which have been fixed and assigned 10 CVEs. Based on the root causes, we categorized this out-of-bounds bug into 3 types. The first type is when there are no checks for layout we talked about before, and when existing checks can be bypassed. The second type is when a fixed size member is used to validate the variable part, but the code doesn't make sure that the fixed member itself is within the valid memory before accessing. The third type is the elements in such arrays use an offset member to locate a variable part, but the offset member is out of range. All right, here's an example of type 1 issue in BTRFS. We choose this one because it's different from other type 1 issues, and there are some ideas worth learning from. Okay, the B tree in BTRFS provides a generic way to store a variety of data types, such as inode files, directories, XATTRs, and more. The implementation of a leaf node is a structure called BTRFS leaf. It contains 2 members, a header and a fixable array member called items, which is an array of BTRFS items. As the code comments explain, a leaf node is divided into 2 parts, item area and data area. In between is unused free space. And each item contains an offset member that is used to locate its corresponding data in the data area. Take a look at this diagram. The header contains a member called NR items, which indicate the total number of items. Each item has 3 members: BTRFS disk key, offset, and size. Using offset and size, we can find corresponding data, and the type member in key indicates the data type. As you can see, the item area and the data area grow toward each other. So the first item corresponds to the last data, and this pattern continues for the rest. The type of data is determined by the type member in the key, with this design, a leaf node can store different kinds of data. Here are some examples, such as inode reference, dev item, and so on. But for now, we will focus on one specific type, BTRFS dir item. It represents a directory entry in BTRFS. So we know that for performance reasons and other factors, the size of memory allocation is not the same as the structure. In this case, the memory representation of a leaf node is called an extend buffer, or EBE for short. When the kernel needs to read or modify a leaf node, it first allocates an extend buffer, then reads the leaf node data from the disk image into that buffer. After that, access to the leaf node is done through the extend buffer. And all the corresponding access interfaces are defined in the file, accessors.h. Now for this layout, because the data area is at the end, so we can simply assume that the layout is already reached the end of the memory. And if there is an out-of-bounds bug in certain data area, we hope it's the last data, which is the data 0, so that it can trigger a KSON report. Of course, this is only to ensure we can catch the bug. However, if the bug happens in the middle of the data area, we might still be able to use an out-of-bounds write primitive to modify the content of adjacent data, potentially leading other impact. The layout of BTRFS dir item is an array of variable size elements. This layout looks very similar to XATTRs because an XATTR is a key value pair. It has 2 length members, name length and data length. So it's clear that this kind of layout works well for XATTRs. And it also makes sense for directory entry. We can set data length to 0 and just use the name length to represent a file or directory. Next, let's look at the iteration in the function BTRFS match dir item name. This function goes through all the dir items, searching for one that matches the given name. The problem is there's no check to make sure that each dir item is within valid memory bounds. So let's try to build poke. First, as we mentioned earlier, to get a KSON report, we need to trigger this out-of-bounds at the end of extend buffer. That means we need to place our poke in the last data. We choose data 6 here, which contains the default dir item pointing to the root item. This way, the mount process will automatically parse that data without any file operations. Second, we only left 1 byte of memory for the last item, which isn't enough for it to be used. And then we need to modify the object ID. Because each item's ID must be smaller than the next one, we have to make sure they are in order. In addition, we update the root dir object ID in superblock, so it matches the object ID of the default dir item. Finally, we fix all the checksums. But unfortunately, we failed. The reason is that there's a check function called check leaf item before the iteration. This function checks all the types of data. You can see that when the data type is either XATTR item or dir item, it calls the same check function, check dir item, because their layout are very similar. After looking into this function, we realized that everything was already being checked. However, when we look at the caller BTRFS check leaf, we notice an interesting flag called written. In short, this condition was introduced in commit at the 2023. In debug case, there might be item data that isn't fully consistent yet. So this flag is used to identify whether the data is consistent. If we don't set this flag in the leaf header, it will skip the check. For now, this case no longer exists, but the code still does. So here's our final poke. We just need to remove the written flag from the header as one extra step. Now we can successfully mount a crafted image and trigger this out-of-bounds bug. All right, this is type 1 issue. There's a missing check both before and during the iteration over an array of variable size elements. Okay, next is an out-of-bounds bug in XFS, and this one is a type 2 issue. Let's dive straight into the key part. The layout of directory entry is a little bit different, and an entry can be either a data entry or an unused entry with just marked free space. And the size of both types of entries is variable. Directory entry can come in different formats. When the number of entries becomes large, it switches to the extends format. We won't go into too much detail here, but in simple terms, the existent format means multiple blocks are used for storage. So in this case, the memory boundary is defined at a block level. Okay, let's take a look at the iteration code in the function xfsdr3 data check. We can see that the condition looks similar to a type 1 issue. When accessing the free tag member in an unused entry, it can already trigger an out-of-bounds access. The difference is there is a check code. This check uses the length member to validate the total size of the entry, but it doesn't ensure the length member is valid. Although this case is also a type 1 issue. In some cases, this check logic will be the first thing done inside the loop. So we classify this as type 2 issue. And again, here is an out-of-bounds read. So a type 2 issue happens when the code uses a fixed length member to calculate the size of the variable part and then checks whether the entry is within valid memory. The problem is the fixed member itself isn't validated. It's a little bit better than a type 1 issue. The code does try to do some validation, but it just trusts the wrong thing. All right, the last case we'll look at is in NTFS3. And this one is an example of type 3 issue, which typically has a critical impact. First, let's talk about the log file. So what's it? The log file is used to store all metadata chains to the file system. It ensures that critical structures can be recovered after a system crash. The layout of log file is shown in this figure. Basically, it made up a series of pages. The first 2 pages are the restart page and its copy. They store basic information, and the remaining pages are used for log record, which we call log record page. The restart page has 2 members used to locate the valid range of the log, oldest LSN and restart LSN. An LSN is like an index for a record. From it, we can get both the record page number and the offset within that page. The oldest LSN points to the beginning of the valid log, and the restart LSN points to the last record. Let's take a look at what a record in the record page looks like. A record page starts with a header followed by multiple records. Each record has its own header called LFS record header, and a variable size record data area. As we mentioned earlier, the last record is located using the restart LSN. In this record, the variable size data contains a structure called NTFS restart, which includes several LSNs. These LSNs point to other records that hold data needed for log recovery. We are especially interested in 2 records, attribute names and open attribute table. For now, we will focus only on understand their layout and not what the data actually represents. First, let's briefly take a look at the memory boundary of the open attribute table. In the variable size part of the record, there's a header called log record header. We use its redo of member to find where the table starts. And then kernel memory dupe function is called to allocate just enough money for that table. And the open attribute table contains a restart table, which followed by many entries. Just like open attribute table, there's an attribute names right after the log record header, and it's also used kernel memory dupe to allocate memory. So the layout is the same. Only the type change, and attribute names also contains many entries. The layout of attribute names looks pretty familiar. Each entry has a variable size name member, and in the log reply function, the code goes through each entry and stops when it sees the off member is 0. But since it doesn't check anything else, if the last entry only has a valid off, accessing other members would go out of bounds. That makes it a classical type 1 issue, but this is not our focus right now. Let's take a closer look at how the code actually works here. For simplicity, we will call the entry in attribute names AN entry, and the one in open attribute table AN entry to load. Here, this function uses the off member in AN entry to locate the corresponding OA entry and then perform some assignments. The off member here is actually an offset relatively to the start of the table. We can see the assignment process has 3 steps. First, the value 2 is written to the attribute name in the right entry. Second, the name bytes in the left entry is divided by the size of a short type, and the result is stored in name length in right entry. Third, the PTR pointer in right entry is set to point to the name in the left entry, which means it's pointing to somewhere in the middle of a heap allocated memory. So the issue is quite clear. The off member is not validated. So if we put a large value in it, it can lead to an out of bounds write on the right entry. All right, we can parse NTFS3 image and set an offset that points outside table to trigger this bug. So we call this type of issue as out of range offset. Now let's summarize the primitives that are available to us. By the way, by that way, we can use these primitives multiple times because attribute names contains many entries, and each one has its own off member that can trigger an out of bounds write. And off member can represent an offset with a 2-byte range. So here's what we get. First, we always write the value 2 at offset 0 from the positions specified by off. Second, we can write any 1-byte value at offset 1. And finally, we can write a pointer at offset 18. This pointer points to the middle of the attribute names, specifically to a name member in AN entry. For the third primitive, in order to figure out which slab our pointer targets and where out of bounds write occurs, we need to know the size of both attribute names and open attribute table. Let me quickly explain what is the slab. The slab allocator is widely used in the kernel. Its purpose is to allocate small fixed-size objects. Each slab is divided into fixed-size objects. So if we know the size of an object, we can determine which slab it belongs to. So we need to figure out the size range of a record. Typically, a log record page is 4 KB in size. If a record at the end of a page is too large to fit, the remaining data gets stored in the next page. So theoretically, the object size could range from 64 up to at least 8K. So the last primitive allows us to write a pointer to an object which can belong to almost any slab into a position that's relatively to the table, and this table can also belong to almost any slab. It's clear that we can use the second primitive to achieve arbitrary value rights, but the problem is the other primitives that end up writing a lot of garbage data before and after it. So a better approach would be to use the third primitive just once. That way we can write a heap pointer of controllable size at offset 0 of an object adjacent to the table, which avoids leaving behind any junk data. A commonly used object that fits our needs is a structure called pool list. It forms a linked list using its first pointer member, and when it's free, the kernel walks the list and frees every pool list in sequence. So we can actually turn our current primitive into a double free primitive. The idea is to use the out-of-bounds right to place a pointer at the start of a pool list, which adjacent to the table, and we choose write a pointer which points an object in kmalloc 19.6. Later, when the mount process finishes, it frees that object. After that, we can reclaim the same slot by allocating a user key payload object. Now, we have a classical double free. The first free happens when the pool list is freed, and the second occurs when we free the user key payload. The next step we want to use is called the pipe primitive, which is based on the dirty pipe vulnerability. The main idea is to modify the flex member in pipe buffer, which allows us to modify a page in page cache so that we can modify read-only files. To do this, we need to perform a cross-cache attack. Because the pipe buffer object lives in a different slab cache. So here is a simple example. For UAF, we can trigger the UAF to get a victim object, and then we can reclaim the victim slab to page allocator. After that, we can get another slab cache to reuse the pages of victim slab. By doing this, we can make victim object to reallocate it as target object. At this point, the victim object is fully overlapped with the target object. Typically, if we get an object that's fully overlapped with a pipe buffer, it would corrupt other members in pipe buffer. So indeed, we choose to use an unaligned overlap, which means our victim object doesn't start at the beginning of the pipe buffer, but in the middle. In this case, we are doing a cross-cache attack from kmalloc 19.6 to kmalloc CG 192. There are two possible layouts, slot 1 and slot 2. But we can only exploit in the slot 2 scenario. So if we hit slot 2, our victim object starts in the middle of the message 1. Now when we free the victim object, the size of the free operation is based on the current slab cache. As a result, it will free half of message 1 and half of message 2. Right now, we have an unaligned overlap between message 1 and the pipe buffer. The first half of the pipe buffer overlaps with the pure data of message 1. So we can read message 1 to identify this situation. Finally, we can free the message 1 and spray enough new messages to reclaim the slot, so we can control over the first half of the pipe buffer, and that's enough to modify the flex member. So here's the final exploit. First, we use an out-of-bounds right to place a pointer to the next member in a pool list. After the mount process, we allocate a user key payload to reclaim a slot. Then we free this slot by freeing pool list. Next, we perform a cross-cache attack to achieve an unaligned overlap between a user key payload in kmalloc 19.6 and a message in kmalloc CG 192. So we free the user key payload to trigger the double free and spray pipe buffer objects to reclaim the slot. At this point, we get an unaligned overlap between a message and a pipe buffer. Finally, we free the overlap message and spray new messages to modify the flags in the pipe buffer. All right, here is a quick demo. Initially, we have a normal user called test. For demo purpose, we use etc sudo er file to grant this user mount capability, and we run our exploit. Now we already modified the password file, and we enter the new password. Now we are root. Okay, let me wrap this up with few takeaways. First, we need boundary checks for the arrays of variable size elements, including fixed members, variable part, and offset. Second, we believe metadata is still a vulnerable attack surface in file system. Third, code review remains one of the best ways to deeply understand a system. You may discover some bugs that fuzzers might miss. And finally, such issues are not limited to the Linux file system. You can apply these same ideas to other targets. Okay, if you have any questions, feel free to contact me. That's it. Thank you.